Okay, welcome everyone to this continuation of diagrams. Diagrams, there you go. Diagrams, diagram algebras, there you go. This video in particular is a continuation of the previous video. Obviously, this is a series, so somehow I assume that you have seen at least a few videos before, but this one is a particular continuation of part 5. So I'm not sure whether you can actually follow if you don't know what part 5 is. You can give it a try. As I said, I'm not 100% sure, but I kind of assume that you have seen somewhat part 5 of this video. Hopefully that is not too much of an assumption. Okay, so let me scroll down. So we have this POTS model, the POTS partition function, and I want to go into a few more details now. And it literally is, you have colored points on a grid. And the colorings, as I was hoping to describe, colors is just a label, right? So you can give it different things. Maybe you can think of it as here 4 different colors, different ways how spins could align or something. Different colors, different spins, something like that. Anyway, we can strip that away and just model it with colors on a grid. Here you have colors on a grid. Okay, cool. And this is called a state. And it's literally, grid is just a graph, so it's a map from the vertices into, oh no, this was supposed to be, so there's a big disagreement of whether you should write that or that. I think in my slides I want to write this, so this should be a capital Q. Don't worry about it too much. So a certain number of Q, the number of colors. Okay, cool. In this example, I guess I have red, green, blue, and yellow, so it will be 4, for example. Cool. And then for each edge you assign a weight, which is the reward you get. Excellent. And it's multiplicative, so different spins give the boring reward 1, and nice spins give the good reward e to the beta, essentially, or for beta it's chosen real number. So depending on how you model it, if beta is minus 500, then this will be small, and if beta is 500, then this will be big. So depending on the model, whatever you do. But roughly that's how it works. You assign a weight to each edge depending on the colorings on the side. Yeah, and that's what it is. The partition function, that's usually denoted by z, depending on the graph, the number of colors, and the edge weights is the sum of all states and then the product over all weights. And this is like the average state, right? You take the sum over all of them, they're weighted by how likely they are, essentially, and this is like the average state. So finding the partition function is a very, very important task in statistical mechanics, okay, in general. So the partition function is the average state. So the system, my model, essentially should somehow converge eventually to the average state. That's what people think, usually do. Also, here I have a capital Q, as I said. Anyway, so this is a partition function. The sum over all states, the product over all weights. Cool. And you want to describe the partition function. That's the goal. And usually that's like very, very difficult to do in one go. So people were historically trying to figure out many, many ways to describe this funny partition function. Okay. And one of the ways to do this is to kind of simplify the problem a little bit, to kind of cluster everything together, and you will get a simpler partition function, essentially. And the way you can try to do this is the following. So here's my little spin assignment, and you can see here, oh, here's a little green cluster. Here's a green cluster. Here's I guess a yellow cluster. And yeah, so you kind of cluster them together as points. Here's a cluster and whatever. So you have, oh, I actually wrote Q here. Excellent. So you have those little clusters, and you kind of break the problem apart into studying how the little clusters behave, right? in this thing. So make the problem a little bit smaller by taking a subset of clusters. Very strict to clusters. First rewrite, restrict to clusters. A second rewrite is the boundary operators. Okay, cool. So essentially we had that in the previous video. Essentially you now take your little grid, you cut it into smaller pieces, and you have some cluster here, and maybe some cluster like here, and now you can draw the operator essentially is now an edge between the two clusters. That's the cuts away this cluster, so the boundary operator is now an edge between those two clusters. That's literally what we're going to do. That's literally what people do. So look at the clusters cut them into smaller pieces, and then the operators is kind of taking the clusters together. Like here's a red cluster, so it's something like that, and has been cut away, something like that, and here's a green cluster, and here's a yellow cluster, something like that. Okay, so that's literally what you do. You get a smaller problem, and you can try to solve that problem. And interestingly, in this case, you get a loop parameter which depends on the number of states in the clusters. So if you kind of compose the operators, you get internal things, and the internal things are the loops that contribute d squared, which is q. So d is square root of q in this picture. So in our little diagram pictures, where are my little diagram pictures? My little diagram pictures are here. In my little diagram pictures. So what it's literally saying is I have some operator that looks something like that, and if I compose them, I get something in the middle. And if you do the calculation, that thing in the middle should be square root of the number of colors. Okay? So that's literally what came out. So they literally computed in this model and studied the operators of the boundary gluing and realized, oh, the little loop needs to be square root of d. And then they went on, and by they I mean this is all in this picture. This paper here, Temperley Lieb. Somewhere here are my first pictures. Where are my pictures? Are my pictures before? Are my pictures later? Who knows, really? Let's scroll up a little bit. There you go. There are my pictures. They literally have those boundary operators, and they try to describe the algebra of boundary operators. Okay, that's literally what they did. And they came up with, okay, they have this diagrammatic description. They're generated by these generators, and they satisfy certain relations, like EI squared. So this is E1, E2, E3, E4. Yeah, so everything is generated by, oh, this could happen, or that could happen, or something like that. Yeah, so that's literally what it is. And the local configuration corresponds to this type of picture, and the EI squared is literally that picture. So EI squared is our little d, which is square root of q, and it's literally solved that. There's a system of equations you need to solve, and you figure out what this algebra is, and that's how they came up with this Temperley Lieb algebra. So the Temperley Lieb algebra is the boundary cut algebra in this system of how the different clusters relate to one another. And then you can use that to essentially simplify the problem of finding the partition functions into smaller pieces. That's literally where it came up from. That's literally how it came up. So essentially that's what it is, and you get diagrams as the boundary state operators. That's not 100% true, because if you really think about this, what you really get is more like the partition algebra, I mean that thing, because kind of clusters can relate, or at least that thing, because clusters can be related arbitrarily, can break into arbitrary pieces if you make it more general. And already in their original paper, they had those empty states, right? So they're not really describing the Temperley Lieb algebra in the original paper. They simplify the problem and then describe what comes out as a Temperley Lieb algebra. In reality, there's a slightly more difficult algebra that appears, which, depending on interpretation of what they do, is either the partition algebra or what people call SO3 webs, whatever that is. Anyway, so let me just say that again. They essentially took this problem, realized that it's a bit too difficult with respect to the methods we had in the 1970s when they wrote this paper. So let's scroll back here. This is 1971 or 70, whatever. And so they could only describe something easier, and they described something easier, which is totally fair. And they ended up with this Temperley Lieb picture, which literally these pictures are just boundary operators connecting certain clusters over, and they satisfy certain relations depending on how the partition function changes. And this is where these diagram algebras came from. Anyway, I hope you enjoyed this video, and I also hope to see you next time.